Welcome to Lagrange Multipliers Part 2. I'm Ronald Johns. Here's what we will do. We will solve an optimization problem using Lagrange multipliers. It's going to be, in this case, optimizing a function of 3 variables and 1 constraint. After solving this problem, we're going to look at the geometry of the situation and realize that our answer does tell us what is happening. So let's see the type of constraint problem we will be encountering. The problem is to maximize the function f of x, y, z, or minimize it, and we'll have a constraint on the variables x, y, and z. G of x, y, z has to equal 0. In this case, we'll use the Lagrange multiplier method. First step is to define another function, capital F, of x, y, z, and lambda to equal f of x, y, z plus lambda times g of x, y, z. Lambda here is called a Lagrange multiplier. So the equations that we'll have to solve are the partial of f with respect to x at x, y, z lambda equals 0. Similarly, for the partial of f with respect to y, the partial derivative of f with respect to z, and the partial derivative of f with respect to lambda. And we want to solve these for x, y, z, and lambda, but we're not as interested in lambda as we are in x, y, and z. So what we have here are 4 equations in 4 unknowns. So let's look at an example problem. Here's what we'll discuss. Maximize this function, f of x, y, z is x squared plus y squared plus z squared, with the constraint on x, y, z satisfying this, x to the 4th plus y to the 4th plus z to the 4th equals 1. So how will we attack this? Remember, we want the constraint to be the form g of x, y, z equals 0. So why don't we do the following? Let's let our constraint g of x, y, z, that function, be x to the 4th plus y to the 4th plus z to the 4th minus 1. I just subtracted 1 from both sides of this equation so that I had a function of x, y, and z equaling 0 on the right. And now our constraint, as I just mentioned, is g of x, y, z equals 0. We'll define this function, capital F of x, y, z, and the Lagrange multiplier lambda to be little f of x, y, z plus lambda times little g of x, y, z, our function that we're trying to maximize or minimize, and our constraint function. So in our particular case for this problem, our function capital F is going to be x squared plus y squared plus z squared, which is little f, plus lambda times this stuff, which is lambda times g. So what we want to do is to solve these 4 equations. This is just the standard equations that we're always going to be solving for this type of problem. So if we look at the partial derivative of f with respect to x, and here's our function here, if we differentiate this with respect to x, we're going to get a 2x, and over here we're going to get a lambda times 4x cubed. So this is going to be 2x plus 4x cubed lambda equals 0. When you differentiate this with respect to y, this second equation turns out to be 2y plus 4y cubed lambda equals 0. Differentiating with respect to z gives us 2z plus 4z cubed lambda equals 0. And when we differentiate with respect to lambda, this equation for this function for capital F, the derivative with respect to lambda of this part is 0. It doesn't involve lambda at all. And here we just have lambda times something. So the derivative of this with respect to lambda is just this something right here. X to the 4th plus y to the 4th plus z to the 4th minus 1. And we also want that to equal 0. Now, if we look at this, we can factor out an x from this side of the equation, rewrite it this way, factor out a y from this expression, write it this way, factor out a z from this one to write it that way, and leave this one the way that it is. So now we need to solve these equations for x, y, and z, and I guess you can say also solve for lambda along the way. But we're really interested in the x, y, z values for this 4 equations in 4 unknowns. So these are the equations that we're trying to solve. If you look at these first 3 equations, we have a factor of 2x here, we have a factor of 2y here, factor of 2z here. If we let x equal 0, then we'll have 0 times something, which is 0. Similarly, if we let y equal 0 or z equals 0, we have something similarly happening with these 2 equations. But then we have to pick x, y, and z so that the sum of their 4th powers is 1. So that's what's ahead of us. How do we solve these equations? Okay, well, as I just mentioned, we could set 2x equal to 0, 2y equal to 0. You can't have z equal to 0 in that case because you want this sum to equal 1. So z has to satisfy x to the 4th plus y to the 4th plus z to the 4th equals 1. Well, if x and y are both 0, what we have in this last equation is 0 plus z to the 4th equals 1, and that means that z has to be plus or minus 1. So we get solutions to the system of equations up here. X, y, and z is 0, 0, and either plus 1 or minus 1. And in that case, our function's value, f of 0, 0, 1, which in our case then would be 0 squared plus 1 squared, or minus 1 squared, they will equal 1. So these are solutions. But instead, we could look at the first and third equations, let x and z be 0, so that these equations are satisfied, and then try to find the y and z that will make this true. And once again, if x and z are both 0, then that's going to force y to the 4th to equal 1, which means that y has to be plus or minus 1, and x and z are the zeros. Similarly, we can find solutions where x is plus or minus 1, y and z are 0. So what happens is we have 6 solutions to the system of equations up here that make f of x, y, z equal to 1. And we'll find out later that this is a minimum. This is actually the absolute minimum value of the function. The absolute minimum value of f is 1 when that constraint is taken into account as we did up here. So, can we get more solutions to this system of 4 equations and 4 unknowns, x, y, z, and lambda? Well, we got the easy ones where we had some of the coordinates equaling 0. So let's see what we can do to find more solutions. We've already taken care of the case where these factors in front are 0. So now the other way to satisfy these equations is to let these second factors equal 0 and also satisfy this constraint. So the second factor equaling 0 is this. This next equation becomes this. This factor equaling 0 is here, and then the constraint is here. So we have these equations to solve for x, y, z, and lambda. We're really interested in x, y, z, but along the way we might have to find lambda too to meet our goal. So solve this first equation for x squared. It's just doing what? Subtract 1 from both sides and divide by 2 lambda. So we get x squared is minus 1 over 2 lambda. The second equation gives us y squared is minus 1 over 2 lambda. This third equation results in z squared equaling minus 1 over 2 lambda. Well, that's kind of nice. the equations we started with in this problem were symmetric, and we're getting some sort of symmetry going on here. X, Y, and Z are behaving just like you would want them to, I guess. And this last equation, what can we do with this? Well, we know that x squared is minus 1 over 2 lambda. And so x to the fourth is x squared squared. And so minus 1 over 2 lambda quantity squared is 1 over 4 lambda squared. Similarly, y to the fourth gives us another term. Z to the fourth gives us another identical term. And those have to add up to 1. Well, that's nice. We saw that this can be written in terms of lambda. And now, this plus this plus this, they all have the same denominator. Those add up to 3 over 4 lambda squared. And that has to equal 1. And we can solve this easily for lambda squared. Lambda squared equals 3/4. So once again, we're just maximizing this function, and we have these 4 equations to solve for x, y, and z, and also lambda. So we saw before that x squared plus equals y squared equals z squared was minus 1 over 2 lambda. Well, if we look at this, the square of a real number is never negative. So this quantity right here has to be either 0 or negative, since x squared, y squared, and z squared are positive. These are positive numbers, so this has to be a positive number also. So we have to have then the following. From this equation up here, we've found out that lambda squared was 3/4. And so if you take the square root of this, the negative square root of that, you get minus the square root of 3 over 2. And we took the negative square root because we saw that lambda must be negative. We had to have a negative number here. So x has to equal y, has to equal z, which according to this formula then is plus or minus 1 over 2 times lambda. And what's happening is, since the square of these is this number, then the square root of these is plus or minus the square root of this number. So we have plus or minus, and then the square root of that number here. And this simplifies to plus or minus the square root of 3 over 3. We can see why that happens, because we have 2 times 1/2 here, basically. So we're going to get just minus square root of 3 for this denominator. And 1 over the square root of 3 is the square root of 3 over 3. So x, y, and z can either be plus or minus square root of 3 over 3. Well, in that case, that gives us 8 critical points. X, y, and z have these coordinates. And in each of these coordinates, you can either pick the plus sign or the minus sign. So one solution is the square root of 3 over 3, square root of 3 over 3, square root of 3 over 3. Another solution would be something like minus the square root of 3 over 3, plus the square root of 3 over 3, minus the square root of 3 over 3. So you have 2 choices, 2 choices, 2 choices. That gives us 8 ways to fill in these 4 numbers for a critical point. So at these points, f of x squared plus y squared plus z squared is going to be 3, since remember, we have 3 terms, all of which were the same, and then minus 1 over 2 times minus the square root of 3 over 2. And when you simplify this, what do you get? The square root of 3, because we have 2 over 2 here, and we also have 3 divided by the square root of 3, which is the square root of 3. And we have a minus here, and so that's positive. So that's the maximum value that f can take, and that function f takes the value of the square root of 3 at 8 different points in space. From our previous part, where we found critical points where the value of the function little f was 1, we now see, since this number is bigger than 1, this was the maximum and this is the minimum. We have found all of the points x, y, and z where the maximum or the minimum occur. So what can we conclude? Since the maximum occurs when x squared, y squared, and z squared are equal to this number over here, which simplifies to the square root of 3 over 3, we find that x can be plus or minus the square root of the square root of 3 over 3, similarly for y and z. Notice that if x squared equals this number, then x has to be plus or minus the square root of this number, and that's what we have right here. You have two choices for x, 2 for y, 2 for z, because we have positive and negative square roots of this being involved. And if you can choose 2 ways for the first coordinate, 2 ways for the second coordinate, 2 ways for the third coordinate, that's going to give us 2 times 2 times 2, which is 8 solutions. So there are 8 points where f has a maximum of the square root of 3. We also saw earlier that the minimum value of f occurs when 2 of the x, y, and z values are 0, and the remaining coordinate is 1. And there are, or plus or minus 1, sorry. There are 6 critical values of this type, where x and y are 0, z can either be plus or minus 1. Similarly, in this one, you have the x value being plus or minus 1, and here the y value being plus or minus 1. And here is the surface x squared plus y squared plus z squared equals 1. It is a sphere of radius 1 centered at the origin. Here is the surface x to the 4th plus y to the 4th plus z to the 4th equals 1. As we can see, it looks something like a cube with rounded edges and corners, something like a die, one of a pair of dice. And this is the surface x squared plus y squared plus z squared equals the square root of 3. This is also a sphere with radius the square root of the square root of 3. Here we see the 3 surfaces plotted together. We have an inside sphere in red, that's of radius 1. We have an outside sphere in, I guess, light green, that has a radius of the square root of 3. And we also have the dice-like object, a pseudo-cube in a way, that's nestled in between them. Basically, that pseudo-cube circumscribes in some way the inside sphere, and it's inscribed into that outer sphere. For this cube, or pseudo-cube, it does touch that outside sphere in some points, and also in the faces of that die, that piece of dice, the middles of those faces touch the inner sphere. And that's why we have the minimum and the maximum for that function f of x, y, z that we looked at. So geometrically, we can interpret what's happening this way, which is quite nice, I guess. It actually shows what's going on, at least geometrically, in this Lagrange multiplier problem. A function to maximize or minimize, and in this case, with one constraint, and we're looking at functions of 3 variables.